music and added some like little All right, let's get started. We got a lot of announcements here. um, on Friday, we're going to work another Water Gems example just to kind of lock in some of the things that we went over in our previous time interacting with Water Gems. So bring your laptop on Friday. And remember, you've got until 11:59 p.m. And I think that's 11:59 and 0 seconds. So that's not 11:59 and 59 seconds. So just be aware you've got till the end of the day minus 1 minute on Friday, March 14th. So that's this Friday to turn in phase 1. So remind me, what are you submitting for phase 1? There's 3 main pieces to the puzzle.
The
Summary table,
the hand
and
calcs,
calcs,
and
write-up. And so the write-up should have documented sources of data that you've gone to kind of justify your estimates. And it should be a written narrative that somebody who's not familiar with this project could kind of get the gist of what you've tried to do. So like think that you're writing to somebody who is technically oriented, but they don't know anything about this assignment, and they're just kind of interested to know like what's the point, what's the objective of what you're doing, how did you go about it, what are the sources that you've consulted, and so on. All right, so any questions about the announcements so far? So that takes us through the end of this week. Next week, I'm sorry to say, we're not going to have any classes. No classes scheduled, so you'll just have to find something else to do next week. Maybe volunteer, go somewhere warm and console yourself that we're not in class. All right. But things really accelerate after that. I've told a lot of people that April is my busiest month, and I think it's starting to bleed over into March. You're going to feel it too. Homework 8 is due on Monday after spring break. And then what I do is for the second half of the class, I try to make the assignments a little bit smaller. So you know how in some of Dr. Michelson's classes, he's got homework every single lecture? Well, we don't quite do that, but it is more frequent in the open channel part of the course. So you'll notice that you've got 2 assignments the week after spring break, and that's because they're a little bit smaller, and I've tried to just carve it up somewhat differently to fit in the assignments while you're in parallel working on the design project. So phase 2 of the design project was related to the pipe network optimization. That's due on March 31st. So really, in terms of the time you're going to spend on the project, phase 1 is the most labor intensive. And it progressively becomes more fun and more interesting if what you really like is tinkering around with pipe sizes and optimization. I think you'll find phase 2 of the project to be just a joy, like working with Water Gems, and it's doing all the calculations for you, and you're just kind of trying to find the best network. So any questions on the announcements? All right. So chapters 10 and 11 of the book were mainly addressing issues related to steady, uniform flow. Now in chapter 12, we're moving on to some of the ideas we have to understand in order to predict the flow depth when conditions are not steady and uniform. So if we had a channel like this, I think this photo was taken in the Central Valley of California. A very productive agricultural region, grows most of the country's fruits and vegetables are from the Central Valley of California. Now not, the cereals and grains like corn, wheat, soybean, that's grown mostly in the Midwest, but fruits and vegetables, a huge portion of it comes from Central California. And they largely irrigate those fields from snowmelt, which is from the Sierra Nevada mountains captured in a series of dams and then taken to the Central Valley through open channels. And so farmers have rights on how much water they can take out of these canals. And so they may have rights that would entitle them to, for example, 8 hours of flow 2 days a week. So they'd open up the gate and send water through a channel like this, flood the fields. That's mainly how they irrigate in Central Valley of California. And this looks like a prismatic channel. See how it appears to be concrete? Its profile is very straight. And so it's unlikely that the channel characteristics are going to cause non-uniform flow. Non-uniform flow being some sort of a disturbance in the direction of flow, like maybe the channel width is changing, or the slope is variable, or there's some obstruction like maybe a pile of rocks in the channel. This isn't going to be experiencing any of that. And so for a channel like this, we could easily just predict the relationship between slope, roughness, cross-sectional geometry, meaning how wide it is, the shape of the channel. All of those factors tell us the capacity of the channel, what Q can be carried for a certain depth. And so it would be easy to determine this, well, relatively easy as trapezoidal geometry ever is. We just use Manning's equation for the steady uniform flow case. Believe it or not, that's the easiest thing that we can use to determine the flow rate. When conditions are unsteady or non-uniform, then Manning's equation won't apply. Manning's equation simply wouldn't give us the right answer for predicting what is the flow rate, because there's some other factor that's changing the flow conditions beyond what Manning's equation handles. Manning's equation is just looking at what would the flow depth be because of the shear stress that's applied by the channel material. You know, like there's some energy loss as the water's flowing downstream. That's in equilibrium with the friction that's imparted is in equilibrium with the elevation change. And so Manning's equation just tells us how deep is the water because of the effect of friction with the pipe, with the channel material. But there's a lot of other things that can affect the flow of water. For example, if you have a channel that's approaching some sort of a steep drop-off, like a waterfall, Manning's equation is going to be able to tell you what is the depth at a certain location if that's what's happening. So we need some additional tools to be able to predict the depth when we have unsteady flow. Unsteady means conditions are not steady over time. Or if we have non-uniform flow. And non-uniform means that in the direction of flow, as we're going downstream, if conditions are non-uniform, it means that there's some sort of a change in either the width of the channel or the slope, or there could be an obstruction like a pile of rocks at the bottom of the channel. Those are the things that would cause non-uniform flow. So the place that we start at in analyzing conditions that are unsteady or non-uniform is we can assess the amount of specific energy in the water at a given location. Specific energy is just defined as the depth plus the velocity head. And you'll remember from previous occasions that sometimes instead of expressing the velocity head as v squared divided by 2g, it's sometimes advantageous for us to express the velocity head as q squared divided by 2g a squared. And the reason why is sometimes we don't know the depth. Sometimes y is unknown, and then if y is unknown, then v is unknown. And now we've got two different unknowns in the equation. Whereas if we express the velocity head in terms of y, then there's just still only one unknown variable in the equation. That is y. So a lot of times you'll see me make this substitution. I'll just say q squared divided by 2g a squared when we're calculating the specific energy. But you'll notice specific energy doesn't have an elevation term in it above some datum. This is just measuring how much energy is in the water above the bottom of the channel. So it's the flow depth and the velocity head. So consider some channel that's 4 meters wide. We're going to go through kind of like an illustration of specific energy and how there's really an infinite number of depths that the water could be going at for a channel that's 4 meters wide, even if it's carrying a certain flow rate. So for example, 10 cubic meters per second, so that's Q, and the width of the channel is 4. So at one end of the extreme, we could have a really steep channel, and if the channel is steep, then the velocity will be going fast and the depth would be low. So that's one extreme, is you could have really fast moving water, so that in order to achieve a flow rate of 10 cubic meters per second, the depth would be low. Another end of the extreme is, what if we had a shallow slope, meaning it's relatively flat, and the velocity is moving slowly? Then the water depth would be larger in order to achieve 10 cubic meters per second. Okay, so conceptually, hopefully that makes sense, that the slope governs the depth, and there's also a relationship to velocity there. And the combined cross-sectional area multiplied by the velocity is what gives us Q. All right, so this table starts off with, let's just say, for this channel, which is 4 meters wide and it's rectangular, just so that the math is a little bit easier for us in calculating the area, for example. The area will just be 4, the width, multiplied by the depth. So this table is showing for just a variety of different velocities, and all of them have the same flow rate of 10 cubic meters per second, then what would the area need to be in order to have V equals, well, actually Q equals V times A? So for example, if we're going to get 10 cubic meters per second and the flow velocity is 10, then that means the cross-sectional area would just be 1 square meter. So this is the fast-moving flow, which would be associated with the really steep channel. At the other end of the spectrum, if you've got a velocity of 1 meter per second, and it could even be slower than that, you know, the flow velocity could be 0.1. So we're just using these as an illustration of the relationship between area, velocity, and flow rate. So you can see I have kind of blanked out some of these values. So what would be the flow area for this one with the green arrow? All right, so calculate that. The area is Q divided by V. So the area is Q divided by V. So that first green arrow, we're saying it's 10 cubic meters per second, and it's for a velocity of 8 meters per second. So it's going to be 5/4 meters squared. So that's 1.25 meters squared, I think. If my mental math is correct. Then at this extreme, well, the area there is pretty easy to calculate. If the velocity is 1, then the area would have to be 10 in order to get a flow rate of 10 cubic meters per second. What's going on here, this middle arrow? I've selected kind of a strange velocity, 2.905. There's nothing magical about that velocity yet, but it is going to be an important point that I'll illustrate why in just a minute. Okay, so area, you get that column. Depth, for this channel geometry, it's 4 meters wide and the depth is y. So the depth is just going to be the area divided by 4 in order to, you know, for a given area, what is the depth that corresponds to that? Okay, and the last column in this table, the specific energy, is where I'm adding together the depth and the velocity head. Now, here I've got both Q and V. So I could have had it be V squared divided by 2G, or I could do Q squared divided by 2GA squared. But I'd like you to go through and calculate the area, depth, and specific energy for this middle one, where I've said let's go for a velocity of 2.905. So let me pause for a moment, allow you to calculate the area, depth, and specific energy and see like what's special about that. Why did I single out that particular velocity? See if you can do some pattern recognition and find out what makes it unique. Alpha is the kinetic energy correction factor, and if you have turbulent flow, which we will in every case, then alpha is 1. If you had laminar flow, then alpha is 2. So most of the time, I won't even bother showing alpha in most of the equations. We just assume that it's close enough to 1 that it's negligible. All right, so just wanted to break in with that. Okay, so I've gone through and done the calculations on the board for this velocity of 2.905. So let's try and figure out what made it special. By the way, anybody have a guess on what makes it so special? It is the lowest specific energy. So look at this. At the top of the list where we had high velocity, when you've got a lot of velocity, that's associated with a lot of specific energy. So you've got a big specific energy because of a lot of kinetic energy. And then at this other extreme, you've got a lot of depth, 2.5 meters of depth, not very much kinetic energy at that low velocity, but a lot of depth. So there is some point at which you'll have the minimum specific energy. And it just happens to be this velocity that I selected here, 2.905. Now really what it is, it's not that there's anything magical about that velocity. The so-called magical thing is this depth. 0.861 meters of depth is the depth that's going to give us the minimum specific energy. So this is a dividing line. The minimum specific energy is the dividing line, and anything with a depth less than that, so here's these lower depths, is going to have a fast velocity and supercritical conditions. And anything that has a depth greater than this minimum point here has slow-moving velocity and subcritical conditions. Do you remember I've told you a little bit about subcritical and supercritical. What do we use that to classify? Those are descriptions which classify what? I only mentioned it once, so there's no shame if you don't know that yet. It's the flow regime. Do you remember I showed you a formula for Froude number? So one way to classify the flow regime is the Froude number. The other is the dividing line between this minimum specific energy. And if the flow conditions are such that the depth is greater than the minimum specific energy, which is subcritical, and above this is supercritical. Let me show you if we graphed it. So this first graph, there's nothing that interesting here. This first graph is just showing the combination of depth and velocity. Okay, we don't have a lot to learn from this graph. But what if we were to graph the specific energy as a function of flow depth? Now there is a lot we can learn from this graph, and it's very, very useful in predicting what the flow depth is going to be after some sort of a disturbance. So I've told you about the disturbances that can cause non-uniform flow, like if a channel suddenly gets wider, or if a channel gets narrower, or if the slope changes. A figure like this can help us to know what is going to be the new depth downstream after some sort of a transition that's causing non-uniform flow. So if you look, on the horizontal axis we've got specific energy, so that's E. On the vertical axis we've got the depth of flow. So this is the figure for that last table. It's this table, I've graphed it. And on the horizontal axis, I put E. On the vertical axis, I put this column of Y. So that is just this data graphed. And so in what we just calculated, the minimum specific energy corresponded to a depth of 0.86. So look at that. The minimum specific energy is this point that kind of hangs out the furthest to the left on the specific energy chart. So if you find that point, and then you see, oh, graphically, we could solve this graphically and find out what is the depth, 0.86 meters, that corresponds to the minimum specific energy. And then here, the 1.29, that is the minimum specific energy corresponding to the critical depth. That's what we call this. We call this depth that's associated with the minimum specific energy the critical depth. Sounds really important, and it is. It's very important. The critical depth is critical. You got to know it because it helps you to diagnose what's going to happen when some sort of a flow change is happening. When Manning's equation doesn't do the job, the first thing you should try and figure out is, do you have supercritical flow or subcritical flow? This part's a little bit counterintuitive. The portion of this graph that's below the critical line, so this is the supercritical range, and this is the subcritical range. So the reason why below the critical depth is supercritical is because that's the fast velocities. So super versus sub is really having to do with, think about the velocities, not necessarily the depth. The depth defines the dividing line, but subcritical conditions, which is above the critical depth, is associated with slower moving flow velocity and greater depths. Whereas supercritical flow is any depth that is less than the critical depth. So, how is the water actually going to flow? Like what depth? Because there's a range of them. Here we've just seen that there's like an infinite number of depths that the water could be at if you've got 10 cubic meters per second going through a 4-meter wide channel. So like, how does the water pick which depth to flow at? That's not necessarily a choice, it's just a reflection of the slope and the roughness. So that's really what determines the flow depth that the water does go at. The roughness, the channel geometry, and the slope is one for a given flow section and a given channel material is what determines the flow depth. So any questions so far about specific energy, why we care about specific energy? If I asked you like on a quiz, we don't have quizzes in this class, or do we? I honestly don't remember. We have a couple, right? Mm-hmm. Yes, they're unscheduled. That's right, we do. We have quizzes, and it's been a while since we had one. So if I asked you, like, why does specific energy matter? Like, what's the utility of it? What's the use of specific energy? Hopefully what you'd be able to say is to help diagnose the flow regime when conditions are unsteady or non-uniform, to help predict what the new flow depth is going to be when Manning's equation won't work. So if you notice on this figure, if we were to pick a certain amount of specific energy, let's say 2 meters of specific energy. If I said there's 2 meters of specific energy in the water, if you go up, it crosses the line, it crosses this curve in 2 locations. There is a supercritical depth associated with 2 meters of energy, and there's also a subcritical depth associated with 2 meters of energy. Those are called alternate depths. There's going to be 2 different depths that have the same amount of specific energy. And you'll have to trust me for now that that's significant and important. It'll help us to figure things out later on. Like if you've got water flowing underneath a gate, like if you're opening some sort of a gate to let irrigation water into a canal, water backs up behind the gate, and then it flows under the gate at a really high velocity because of the pressure on the other side of the gate. Well, these alternate depths will help you to find out what is going to be the flow depth upstream of the gate and downstream of the gate. That's just an illustration of how this information is going to be useful. We're kind of just like learning the terminology, learning some of the calculations today, and then we'll get into the applications over the course of the next several lectures. So just to reiterate some of that terminology, there is some minimum specific energy that's associated with the critical depth. So critical depth is that far left side of the graph. And when your flow depth is more than the critical depth, that's subcritical conditions. Sub meaning kind of like slow moving. And that's what you'd have for a large water depth. You'd have relatively low velocities. When the water depth is less than the critical depth, that's supercritical conditions. The water velocity is fast. We could also determine the top width of the channel under critical conditions. And so you may see B. Now, uppercase B means the top width of the channel. Lowercase b means the bottom width of the channel. If we've got a rectangular channel, like we've been working with so far, then the bottom width and the top width's the same. But for a trapezoidal channel, that's not the case. But anyhow, sometimes when you've got critical conditions, you may need to know what's the top width under critical conditions, and that's B sub C. So here, B sub C would be 4 meters because the width of the water in the channel is going to not vary as a function of depth. But for a trapezoidal channel, it does depend on the depth, and it also depends on T, which is the slope of the side angle. All right, so here's another version of the Froude number equation. This looks a little bit differently from what you've seen before. This is saying that you can determine the Froude number by knowing the flow rate squared, the top width of the channel, G, the gravitational constant, and then the cross-sectional area of the channel. So this always works. There's a few versions of the Froude number equation I'll show you that only apply if conditions are, if like you've got a rectangular channel. But this version of the Froude number equation works regardless of the geometry. So this one will never lead you astray. It'll always work. And what we want is FR. So you'd have to take the square root of both sides of the equation to get Froude number. This is Froude number squared is Q squared divided by times B divided by G A cubed. So Froude number would be the square root of this right-hand side term. If the Froude number is less than 1, that's subcritical. Greater than 1, that's supercritical. That you already did know from that homework hint I gave you last week. Classifying the flow regime. Flow regime is either subcritical or supercritical. I think we've briefly talked about hydraulic depth before, so here's just a refresher about that. Hydraulic depth is the area of the channel divided by the top width. Some books would call hydraulic depth, they'd assign that the variable d, which is a little confusing because sometimes we use d for diameter, right? So other books instead have called the hydraulic depth y sub h. But if it's described as the hydraulic depth, it's asking what would the equivalent depth be if it was a rectangular channel. So this ratio of the channel area to the top width is kind of like a way of taking a trapezoidal channel and expressing what would the depth be if you instead took this trapezoidal channel and found an equivalent rectangular channel. How deep would the flow be? So in a rectangular channel, it's easy because the hydraulic depth is just the same as the depth itself. And we went through that derivation before. But this is kind of an interesting thing, is that if you have a really wide channel, then the hydraulic depth is equal to the physical depth, regardless of what the shape of the cross-section looks like. And that's because the side area is negligible if you've got a very wide channel. And what we mean by very wide is that its width is more than 20 times greater than its depth. That's kind of a technical definition of very wide. So let me show you an illustration of what this means about how the hydraulic depth is just equal to the physical depth for a very wide channel. So this is just showing a channel that is very wide. Now the reason why the hydraulic depth is equal to the flow depth for a very wide channel is that the flow area of these side triangles is so small compared to the flow area of the main rectangular portion of the channel that like whatever flow area is being contributed by these side portions can be neglected if it's very wide. So remember, hydraulic depth is just expressing a trapezoidal channel in terms of what its depth would be if it was rectangular. What we're saying is if it's very wide, that's more or less rectangular, just because its width is so much greater, like the wetted perimeter at the bottom of the channel is so long compared to the minor and inconsequential wetted perimeter at the side edges. So of a rectangular channel, it is the physical depth, and for a very wide channel, it's also the physical depth. But keep in mind that you sometimes have to double check how wide is the channel compared to the flow depth, and is it more than 20 times greater? If so, then you can make that assumption about the hydraulic depth. Okay, so let's use some of these ideas about subcritical versus supercritical to diagnose the flow regime using the Froude number and by looking at the graph. So here's the graph. So this is the same figure that we have looked at a couple times before. It's the graph of the table from the beginning part of the class. So what we know is that the critical depth was 0.86. Okay, so what about this case? If the flow depth is 0.25, so 0.86 is the critical depth. For a flow depth of 0.25, that's less than the critical depth, and so that's supercritical conditions. Now, double check that. Calculate the Froude number. So the Froude number, FR, is the square root of Q squared times B divided by GA cubed. All right, so if we've got 10 cubic meters per second, B for this rectangular channel is 4. Okay, so it's the square root of 10 cubic meters per second squared times 4 meters is the width divided by G, 9.81 meters per second squared. And then the cross-sectional area, if the flow depth is 0.25, so that is a flow depth of 0.25 meters, and the width of it is 4 meters. And so the area is 1 square meter. 1 meter squared, and we cube it. Okay, what's the Froude number? Anybody get 6.39? Okay, so when the Froude number is greater than 1, it's supercritical. So we can diagnose the Froude number either by comparing the given flow depth of 0.25 to the critical flow depth, or we can diagnose the flow regime by the Froude number. So let me write that on the board. Since y equals 0.25 meters is less than yc of 0.86 meters. So since the given flow depth is less than the critical depth, then the flow is supercritical. I think that should always end with an exclamation mark. Supercritical, exclamation mark. All right. Or the Froude number, let me bring the calculations up on screen just to illustrate. Subcritical, you don't have to put an exclamation mark with that. Okay, so almost there. All right. So the Froude number, okay, so this is one way we diagnosed supercritical. This is method number 1. Method number 2 is since Froude number of 6.39 is greater than 1, then flow is supercritical. All right. Now, what about this other one? This second case here. The flow depth is 1.25. Is the flow supercritical or subcritical? Well, since we already have a graph of specific energy, we don't even have to do calculations. We could just look at the graph of specific energy and say, by inspection, it appears that the critical depth is about 0.8606. And since the depth of 1.25 is larger than the critical depth, thus it is subcritical. So, I mean, it wouldn't always, like on an exam, be bold like that to tell you the answer straight away. But what you could say is you can diagnose the flow regime either by comparing the flow depth to the critical depth or by calculating the Froude number. So since y equals 1.25 meters is greater than yc of 0.86, then the flow is subcritical. Or the other way to do it is the Froude number. So the Froude number is the square root of q squared times b divided by g times a cubed. And we still have the 10 meters cubed per second. Square that. It's still 4 meter wide channel. G is still 9.81 meters per second squared. The only difference now is that the area, if the flow depth is 1.25 and the channel is 4 meters wide, so area is 4 times 1.25 5. My brain's not working too good today, guys. I should have been able to do that one in my head. You should have shouted it out so I didn't have to use my calculator. 5 square meters. It is 5 square meters, and we cube it. So let's see. What would be then the Froude number there? 0.571. So the other way to assess the flow regime is, since the Froude number of 0.571 is less than 1, then flow is subcritical. All right. Any questions about specific energy, subcritical versus supercritical? Could you graph specific energy if you were asked to? Could you take a flow, like a channel, and a certain flow rate and make a table out of it like this? I bet you could. I bet you could. All right. So, alternate depths. Alternate depths are those points on the figure that have the same amount of specific energy. Two different depths that have the same specific energy. So E, the specific energy, is the depth plus velocity head. And velocity head is either v squared divided by 2g, or we could calculate the velocity head by q squared divided by 2g a squared. So what is the specific energy when the depth is 0.5? Okay, so let's do this graphically. 0.5, so I'm starting right here. I'm going over to the side and then down. It looks like that's associated to a specific energy, if I start at 0.5, go over and down, I don't know, 1.6 meters of specific energy. So what is the other depth associated with that same amount of specific energy? So graphically, I can estimate, okay, if I go over here and then up, straight up, it's going to be like, I think the other depth is going to be around 1.5. I don't have a ruler right now, so I can't draw as straight as I'd like. But if I go over, here's one of the depths. The other depth is straight up, and then we find out about 1.4, 1.5. Well, we can do it numerically. Since I don't have the ruler, we won't do it graphically. Let's find out what is the other depth that has the same amount of specific energy. So the way to do that is find out how much energy is there when there is 10 cubic meters per second going through a 4-meter wide channel, and the flow depth is 0.5. So what is E in that case? Okay, so E is the depth plus Q squared divided by 2GA squared. Okay, so for y equals 0.5 meters, that means if we've got the channel is 4 meters wide still, and the depth is 0.5, then A, I can do this one in my head, A is 2 meters squared, right? Width times depth. So the specific energy is 0.5 meters plus 10 meters cubed per second. We got to square that, divided by 2 times 9.81 meters per second squared. And then the area, 2 meters squared, and square that. So how much specific energy do we have? I think E is 1.774 meters. So that's the amount of specific energy that is present. So the alternate depth, we are going to set it up and find the cubic root. So there is some other depth out there besides 0.5 that has the same amount of specific energy. So E is 1.774 meters, and that is equal to the depth plus the velocity head, Q squared divided by 2GA squared. Okay, well, that is y plus Q squared, so that's 10 squared divided by 2 times 9.81. What's the area? Area is 4 times y squared. Since we're running low on time, let me show you these calculations. You can be assured that solving for cubic roots in an equation is going to be something you'll get very good at. We're going to do it a lot. So on the left-hand side of the equation is the specific energy that we've just calculated, the same one that's associated with the depth of 0.5, 1.774. So Q squared divided by 2GA squared. All right, so let's combine all of these numbers together and we get 0.3186 divided by y squared. Multiply each term by y squared to get it out of the denominator. So 1.774 y squared is equal to y cubed plus 0.3186. Rewrite it, and then in your calculator you should be able to solve for roots. We get a negative root, which we can throw away. There's no such thing as a negative flow depth. We get a depth of 0.5, which we already knew that was one of the depths that can give you that amount of specific energy. And then here's the other one, 1.66 meters. So this is the supercritical depth for that amount of specific energy, and this is the subcritical depth for that amount of specific energy. So the question was asking, What is the alternate depth? The alternate depth is the depth that has the same amount of specific energy, 1.66 meters. And we found it by solving this cubic equation. All right, we got to leave it there for today. It's 11:50. Remember that on Friday, you should bring your computer to class with WaterGems installed. I'll see you then.